Okay, now please stand the line. A lot of this ones. Nine eight two eight seven. Okay, thank you.
Please stand
Please
the
stand the
line.
line.
Okay.
Chaos.
Micro.
Micro.
Hello? Please respond here. Can you hear me? Okay. Students, listen carefully. See this one. This is the unit 2 basis and dimension. Now already we have explained here linear dependent and independent of this part. Okay. See this one. Now, what is the linear dependent independent of this part? So here x being any one of the vector, that vector is an equivalent to write the linear combination of the value, that is a1 x1 plus a2 x2 plus and so on an xn. This is the linear combination of this part, and that linear combination must be equating to 0. 0 means that is the each and every scalar, not all 0 is there. Enter the combination must be an equating to 0 vector. Now to write as a0 x0 plus a1 x1 plus so on an xn equal to 0. And according to that, we have to see and refer this one. This is linear independence through the linear combination of the vector. So enter the linear combination combination of the part is an equating to 0. Each and every scalar must be 0. Each and every scalar 0 means if a1 equal to 0, a2 equal to 0 and so on an equal to 0. So because when the each and every scalar must be equating to 0, that is called linearly independent. So some scalars are 0 but not all 0, that is called linearly dependent. So that is the difference between dependent and independent through the linear combination of this part. When the linear combination a1 x1 plus a2 x2 plus so on an xn equal to 0. Because enter each and every scalar of the 0, that is called linearly independent, and some scalars are 0 but not all 0, that is called linearly dependent. Okay, linearly independent means each and every scalar through the linear combination to write as the summation ai xi equal to 0 for all ai equal to 0, here I varies from, just you have to see and refer here, I lies between 1 to n, because a1 equal to 0, a2 equal to 0 and so on, an equal to 0. That is called linearly independent. But not all, but scalars not all 0, that is called linearly dependent. Now same definition, we will refer through the matrices, because given the all the vectors, given the vectors must be arranging as the rows. Okay, suppose there are 3 vectors here, x1 be one of the vector, x2 is also one of the vector, and x3 is also another vector. There are 3 vectors are here, each and every, because here to write as we are taking the 3 rows. Okay, x1 vector to write as the first row, x2 vector to write as the second row, and x3 vector is also to write as the third row. So when the determinant must be please excuse me, then their determinant must be equating to 0 is called to find the determinant of the given the vectors through the matrices of the part, because when the determinant is not equal to 0, that is called linearly independent. When the det equal to 0, that is called linearly dependence. That is the through a difference between the linearly dependence and independence through the linear combination and linear combination of vectors, and that is also in the same manner to verify through the matrices of the determinant. Okay, so that is the difference between the linearly dependent and independent. So what are the standard vectors? Standard vectors are represented as e1, e2, so on, en. Just you have to see and refer here. Students, listen carefully. This is one of the famous example, 2.2.2. Okay, so what are the standard vectors on the dimension of this part? Now it read as nth dimensional, n dimensional of a vector space, means n tuples of the vector space, means r power n. Okay, now n dimensional of the n tuples of the dimension of real numbers of a vector space denoted by r power n, means it read as n dimensional of a vector space over the real numbers. What are the standard basis? E1 is the first standard base or standard base. There are similar names, usual basis, standard basis. Okay, or what are the usual basis? E1 equals to 1, 0, 0, so on 0. This is the n tuple of the first dimensional of standard vector. Okay, for standard vector, standard basis of a vector. E2 is when the second dimension is unity and all the remaining dimensions are 0, that is called second dimension, second standard basis of a vector. Up to n dimensional standard means 0, 0, 0, so on, 1 is there. Now, it read as a standard basis. All the standard basis are when the n tuples of the vector space is denoted by r power n, is also a basis of a vector space, because that is linearly independent of this part, because each and when the first dimension is 1 and second dimension is 1 and the third dimension is 1 and up to nth dimension is also unity, all the bigger remaining all the dimensions are 0, because first just you have to see and refer here. That is the first standard basis of a vector is 1, 0, 0 and so on 0, because when the x dimension, first dimension is 1. Okay, and vertical axis, second dimension, means the second coordinate of the vector is 1. And third coordinate vector E3 equal to 0, 0, 1, 0, so on 0. That is the third coordinate vector, because the third coordinate vector means the third dimension is unity. Up to nth dimension is unity. Now it is denoted by E1, E2, so on, En. Okay, these are all standard basis of a vector space. Then automatically all the standard basis of vectors is linearly. So all the standard vector space, standard vectors are usual vectors. It read as standard vectors are usual vectors. In the usual vectors, it is a linearly independent, because when the linear combination through the standard vectors a1 e1 plus a2 e2 plus so on an en, all the ai values are scalars. Here through the standard vector means e1 e2 so on en, to write as the linear combination when it is an equating to 0, because a1 0 0 this value A1 means A1 E1 means A1 of 1 0 0 so on 0, A2 E2 means A2 of 0 1 0 so on 0 so on. This is AN of 0 0 0 0 1. Now then the value is, it is an equating to 0. Each and every scalar is 0 because null vector can also be written as 0 0 0 so on 0 is there, because A1 equal to 0, A2 equal to 0 and so on, AN equal to 0. So then automatically each and every scalar must be to 0. That is called linearly independent. Now this is one of the important concept is there. You have so all the standard vectors or ORR usual vectors, it is always linearly independent. Now that is the base concept of basis of a vector space is, given the subset of a vector is linearly independent. That is the first principle of basis of a vector space. Now please take care to check. Okay. Now given all the subset of a vector space is linearly independent. Second condition is when the linear span must be a vector space. Linear span means L of S equal to V. Given the capital S is linearly independent and the second one is L of S equal to V. Now that is called basis of a vector space. Now this is one of the important concept. Don't forget this one, because what is the basis of a vector space? Just you have to see and refer here. Students, please listen carefully. This theorem through the linearly independent. Okay. 2.2.6. Now one of the important theorem in the final examination, because let V be any one of the vector space over a field capital F, and given the subset can also be given the subset of a vector space is set of x1 x2 so on xn. Then capital S is linearly independent over capital F if and only if every element in the linear span L of S, it has a unique representation in the form A1 x1 plus A2 x2 plus so on AN xn. All the xi values are subsets of the values and all the ai values are field elements. Okay. Next, see and this is then the proof is, first of all, to write as the linear combination. So x equal to A1 x1 A2 x2 so on AN xn. So enter the part is can also be written as summation ai xi. Okay. Now in the suppose we are taking the another scalar part is bi values. To write the another one is x equal to b1 x1 plus b2 x2 plus so on bn xn. So both are, it is an equivalent. So summation ai xi equal to summation bi xi. Now can also be written as a1 minus b1 of x1 plus a2 minus b2 of x2 so on an minus bn of xn equal to 0. Because so that finally it is given here, given the vectors of the subset capital S is linearly independent, because a1 minus b1 equal to 0, a1 equal to b1. So that is the unique scalars. So a2 minus b2 equal to 0, when then automatically a2 equal to b2. So at the same time a2 equal to 0 or b2 equal to 0. So all the scalars must be an equating to 0 to write as the concept through the linear combination. Finally, we are getting that all the scalars, each and every scalar must be 0 is here. So that is the unique representation of the form. Okay. Now to write as the converse part. Okay. Okay, that is the simple theorem 2.2.6. Next one. Now, please note down. Another one. What is the basis of a vector space? Already, we will discuss. This is the concept of basis of a vector space. So, given the subset of the vector space linearly independent. Okay, see here. There is a simple theorem is there from the definition of basis of a vector space is, just you have to see here 2.3.1. Let V be any one of the vector space over a field capital F. Here capital B be any subset of a vector space. So that subset is taken. So in the replacing of capital S by B. So some others referred as capital S is there. S be any one of the subset. But in your university material, capital B be even here, B be a subset of V. So then capital B is called a basis for capital V over F. So if capital B is linearly independent over capital F and the linear span L of B equal to V, because linear span is denoted by L of S or because B be the subset given here. So that's why linear span under the capital B is the subset is L of B. When must be to form a vector space. When these two conditions are satisfied, that is called basis of a vector space. So what is the basis? Linearly independent condition must be satisfied, and the second one, linear span must to form a vector space. When these two conditions are satisfied, that is called basis of a vector space. So from the basis of a vector space, this theorem is also very important in the examination 2.3.2 and 2.3.3 is very, very important, because please note down here, suppose capital B equal to one of the basis of a vector space. B is given. Hello? Can you hear me? Okay. Suppose capital B equal to set of x1, x2, so on, xn is a basis for a vector space capital B over a field capital F, and set of y1, y2, so on, ym, it is a linearly independent set in capital B, then m is less than or equal to n is there. Okay. Now, here what is the basis of a vector space? Now, there is given the notion, it is represented as capital B equal to set of x1, x2, so on, xn. Now, this is the consider of the part. Okay. Now, given the vectors to be represented as the basis of a vector space, and here set of y1, y2, so on, yn in the same manner, it is also a linearly independent set in capital V, because given the set is represented as in terms of n consisting vectors, and another one is m consisting vectors. So then automatically n less than or equal to m and m less than or equal to n. So finally m equal to n is there. Okay. Now, this is also one of the important theorems to listen carefully. 2.3.3. This is also one of the important theorem of it is completely based on the basis of a vector space. Okay. Next, another one. 2.3.5. This is also very simple concept. Any two bases of a finitely generated vector space have the same number of elements. Okay. Any two bases. Finitely, what is the generated of this part? Only one element must be generated given the vector space. That is called generated of a vector space, means that is the simply when it is must be a finite. So that is called finitely generated vector space. There are just you have to form any two vector spaces, it is consisting of any two bases. One is capital N and another one equal to capital M. Okay. When the M equal to N, this is also one of the corollary of from the above theorem. Okay. Let capital V be any finitely generated vector space. That is the simple proof here. Okay. V be any one of the finitely generated vector space over the field capital F. Now it should possess a finite basis. Finite basis means here n consisting of the elements given in the vector space. Okay, capital B equal to set of x1, x2, so on, xn. And C is also another basis. We are taking it, there are two bases here, but because there are two bases of a vector space and it is consisting same number of elements given those bases of a vector space. So then automatically it is also a generated of this part, because that is the representation of a basis capital B equal to n consisting elements. And another one capital C is also other basis. Other basis means then the consisting of the elements is also a what is that, linearly independent and a linear span. So C must be a finite and the number of elements in C must be less than or equal to n, because that is the same argument, n less than or equal to. N less than or equal to. Now this is the mod C. Mod C means the number of elements given in the basis of a vector space. So n is less than or equal to mod C, or mod C less than or equal to n, then automatically n equal to mod C. That is the absoluteness, because it is consisting a number of elements is also same given in the, it is an equivalent to small n is there. Okay. Now, students, listen carefully. This is one of the important example here. What is the complex number of a vector space of the dimension? Okay. This is the complex of a vector space. Then the field elements are also complex numbers. In the arbitrary of the complex numbers of the dimension is always 1. Okay. And arbitrary of the C also over the real numbers of the dimension is 2, because there are 2 dimensions over the real numbers of here. So then automatically C be the complex numbers and R be a real numbers. So R it is also a subfield of C, and C is a vector space over C. Okay. Now, so generate only one element generated, that is the basis for C. So only one element must be generated here. So that's why dimension of the complex numbers is 1, and dimension of the real numbers is through the C of a vector space over the real numbers, then their dimension is 2 is here. When the complex numbers of the dimension is 1, real numbers of the dimension is 2. Okay, don't forget here. Okay. Now, generated is also in sometimes that is called spanning of this part. Okay. Just you have to see and refer this theorem 2.3.9. This theorem is also very important. Let V be a finite dimensional vector space over a field capital F, then any linearly independent set in capital V can be extended to a basis. This is the extension theorem. Title of this theorem is extension theorem. Basis extension theorem or extended to a basis. So this theorem is called basis extension theorem. So that's why finitely just we must assume the vector space is finitely generated, that is capital V. So then automatically it is linearly independent set in V can be extended to a basis. Okay, this is the important theorem, because first of all we must assume that A equal to set of x1, x2, so on, xn. This is a linearly independent set in V. So M is less than or equal to dimension of the vector space over the field. Then suppose, then automatically here the assumption is okay. If A is not a basis, so the linear span, it is not to form a vector space. So L of A not equal to V. So that's why we are just one of the existence element is we must assume that we will assume that x m plus 1, because here m consisting element is there, but extension of the element is m plus 1. So through the vector of the basis element is xm plus 1 is also consisting in capital V. Suppose xm plus 1 is not a linearly combination of the element in A, because this is not a linear combination of the element. So that's why it can also be written as x1, x2, so on, xn and xm plus 1, because n is different, n is entirely differ from m plus 1 basis element. It is linearly independent. This is does not basis, because we get another element is xm plus 2. Okay. So in the same manner, to write as x1, x2, so on, xm and xm plus 1 and xm plus 1, xm plus 2, so on, in between the n consisting of elements, we must assumption of the part is xm plus 1, xm plus 2, so on. So enter all the elements to form a extension of the elements in between the it varies from 1 to n. So in between the elements are m plus 1, m plus 2, that is to write as the linear combination of this part, then automatically it is a linearly independent and a linear span. So those elements does not form a basis of a vector, and to our assumption to continuing of this process and to take the another element is xm plus 2, and then it is also in the same manner does not a basis, and another element is xm plus 2 and another element is xm plus 3. Okay, there are so many elements in between 1 to n. Finally, they enter the in between the 1 to n elements to extend through the extended of the elements to form a basis for vector space. That is the simple proof. You must extended of this concept is according to theory. Now that is the here well established theorem is basis extension theorem, that is 2.3.9. Okay. Next one. Now, this is the simple 2.4.2. That is a simple concept. A dimension of a vector space is denoted by dim capital V. So, V be any one of the vector space of dimension is n. Means dimension V equal to small n is there. It is consisting of n elements given in the set. Okay. So, when that set is not a basis set, means then automatically linear span does not form a vector space. So, L of B not equal to V. So, that's why there exists another element is continuing of the element of n is n plus 1. To write the linear combination, and then automatically when it is not a linear combination of x1 so on xn, and at the same time x1 x2 so on xn plus 1, then it is linearly independent. And suppose to write as the another existence element xn plus 2 is there. So that is not also a linear combination of x1 so on xn plus 1. Then automatically x1, x2 so on xn plus 1, xn plus 2 set is also a linearly independent. This is the contradiction of this part. Okay. This is one of the finest example which are given the vectors when it is linearly dependent and independent. Students, listen carefully here. Now through this one, this is well established example through the basis of a vector space. Before the basis of a vector space, first of all, there are two important conditions for the basis of a vector space. One is given the subset is linearly independent, and the second one that subset of a vector space when it is linear span, means L of S equal to V. There are two important conditions, that is two important conditions for basis of a vector space. Then easily to form a basis of a vector space. Suppose given x1, x2, x3, there are three vectors here. x1 equal to 3, 1, 0, 0 and x2 equal to 0, 2, minus 1, 0. This is the second vector. And third vector is 0, 0, 0, 4. There are three vectors here. These three vectors is consisting one of the set is there. Set of x1, x2, x3. It is also a linearly independent in the vector space. R power 4 over capital R. Okay. Suppose A1, A2, A3. These three elements is consisting real numbers. So A1, x1 plus, A2, x2 plus. So A3, x3. To write as the linear combination must be equating to 0 vector or null vector. So even the each and to write as the replacing of the vectors given this linear combination, A1 of x1 means 3, 1, 0, 0. X2 means see this here. Okay. A1 of given the vectors, that is x1 is 3, 1, 0, 0 plus A2 of x2 is 0, 2 minus 1, 0 plus A3 of x3 is 0, 0, 0, 4 equal to. Hello? Class lo unna even chestam. So A3 of 0, 0, 0, 4 equal to 0 vector. Now to write as here 3A1 and first coordinate is A2 is 0, third coordinate is 0. So again 3A1 equal to 0, then automatically A1 equal to 0 because null vector is 0, 0, 0, 0 because this is the 4-dimensional of the null vector. So and again through the second coordinate, this is A1 plus 2A2 equal to 0. Because already we know that A1 equal to 0, replacing of this equation A1 plus 2A2 equal to 0. So then automatically A2 equal to 0. Okay. And the third coordinate is A1 into 0 and minus A2 equal to 0. Minus A2 equal to 0 means A2 equal to 0. So then finally 4A3 equal to 0. So because when it is the equating to the equal coordinates, so each and every scalar must be 0. Finally, we are getting the given the set of vectors is linearly independent. That is the simple concept. And second way, that is the another root of the problem is also here. Given the vectors must be arranging as the rows for the determinant of the matrices. So to find the when the determinant of the matrix, then it is an equal when the det is not equal to 0 for the given the matrix of the vectors, then automatically when the not equal to 0 means given the set of vectors is linearly independent. Okay, when the det is 0, then automatically that is also to check our convenience. Okay, your convenience, whatever it is. There are two types of problems. Given the problem is there are two types. Okay. Okay, students, this is 2.4.4. This is also one of the important problem. Please note down, because due to our session problem, because this is the third session of the through the online. Okay. Okay. Now that is 2.4.6. Now that is not necessary here. 2.4.5. This is all for your purpose. Okay. Next one. This is the basis and the dimension. Okay. Please stay on the line. Please stay on the line. See this one. That is the one of the important concept is here, because only there are four classes through online is here. Okay. Now this is the third class. Some other important problem will also discussed here. Okay. Unit 3. Please note down. Quotient space. What is the quotient space? That is the unit 3. Quotient space is denoted by V by W. That is the direct concept. Okay. Students, listen carefully. Already, this quotient of a subspace, quotient of a quotient space is also denoted by V by W through the cosets of a subspace. Already we have learned in group theory quotient group, that is G by H. Quotient ring, that is R by U. Okay. Quotient group is G by H equal to set of all right cosets or left cosets given in the set of the roster form. That is called quotient. When the given the quotient set to form a group, that is called quotient group, that is denoted by G by H. Okay. In the same manner, quotient ring is also R by U, because R be any one of the ring and U be an ideal of a ring. Just you have to see and refer in the previous concept, that is the fourth semester ring theory. Okay. That ring theory of the concept, R by U is the quotient ring. And before that, R by U be the set of all cosets. Okay. Either X plus U or U plus X. When the given the ideal of the element, to take the ring of the element at left side for given the ideal, that is called left ideal. At right side of the ideal of a ring element, to take the ideal of the element, because U plus X equal to, then the ring of the element at right side for the given the ideal, that is called right ideal. So set of X plus U or U plus X, the set of all left ideals or right ideals given in the set, that is called cosets of the set. That cosets of the set, to when it is to form a ring, that is called quotient ring. Then automatically we are easily to prove that quotient group of an abelian group is abelian. That is one of the well-established theorem in the group theory. At the same time, quotient of quotient ring, the set of all cosets to form a ring, the quotient of an abelian ring is abelian. So these are all well-established theorems and in the modern algebra part. In the same manner, quotient space is denoted by V by W, and the set of all left cosets. This is the W be any one of the subspace. Just you have to see and refer 3.2.1. W be any one of the subspace of a vector space. So that subspace of a vector space element is to take at left side for the given the subspace, means this is the X plus W. So it read as left coset. Now this is x plus w is called coset of w corresponding to x, and before that w is the subspace of the vector space. To take the element, another element of the subspace is y. So that's why x plus y, such that here y belongs to w. So that is the coset of the part. Okay. Now some other properties, some other properties of cosets. For any x comma y belongs to capital V, V be any one of the vector space. There are two elements given in the vector space, x plus w equal to y plus w. So that's why any two cosets of the elements, when the any two cosets of the elements, when it is and it is also equal, then automatically same subring condition must be satisfied. X minus y is also belongs to w. So the any two cosets of the elements, when it is must be equal, if and only if x minus y is also belongs to w. That is the first property. Second property, the intersection of any two cosets is disjoint. Any two left cosets or any two right cosets, either disjoint or identical. Identical disjoint means here x plus w is one of the coset and y plus w is also another coset. The in between the intersection of their part, that is an equivalent to empty set. So then automatically identical means those cosets are equal. X plus w equal to y plus w. Either this one or this one. Okay. Either this or this. That is the disjoint or identical. To write as the identical. And third condition, here x being any one of the vector, all the either left coset or right coset must be a subgroup. Okay, in the suppose the group theory is there, small h into small h be any arbitrary element, small h capital H and capital H into small h, that is the right coset equal to subgroup capital H. In the same manner, x plus x being any one of the vector, x plus w equal to w. Here x is also belongs to w is there. The union of all cosets of w, their number of cosets are there, because x1 plus w union, x2 plus w union, so on. Enter all the values must be, it is an equivalent to a vector space. That is the simple. These are all four important properties. Okay, from the now it follows the previous concept in group theory. Okay. Now this theorem, quotient. Okay, let W be any quotient space, and before the concept is quotient set, and purely quotient space means through the quotient set to form a vector space, then automatically through the vector addition and scalar multiplication, that is called quotient space. Quotient space is denoted by V by W, and before that this is the quotient set, V be any one of the vector space and W be a subspace. But here the quotient is represented as V by W. When the V by W of the elements means that is the cosets. That cosets is denoted by in the subspace of the vector at right side, where the W be any subspace. That subspace of the vector must be adding at left side. That is called left coset x plus w, such that x being any one of the vector. So we are taking any two quotient space of the elements, cosets of the elements x plus w and y plus w, and in between the vector addition is x plus w plus y plus w. That is the addition of vectors in quotient space. X plus w plus y plus w, that is x plus y of plus w. And second one, a of x plus w, that is this is the scalar multiplication. Ordinary scalar multiplication is ax, but here a be any one of the element, so a of x plus w equal to ax plus w. So under the vector addition and scalar multiplication, given the cosets of the set to form a vector space, then automatically V by W under addition, under multiplication to form a vector space. So first of all, then it is the well-defined of this part. Well-defined means we are taking the same vector of the similar of the vector. Just you have to imagine of the just you have to imagine So image of the element is x dash is there under the process of a vector small x plus w equal to x dash plus w. So that's why already we have proved that the one of the property, any two left cosets are equal, x minus y is also belongs to w. So in the replacing of y by x dash, x minus x dash belongs to w. So then automatically those elements are equal, those cosets are equal under x or y. X plus w equal to x dash plus w, or y plus w equal to y dash plus w. So here x minus x dash and y minus y dash, both elements are belongs to w is there. Okay. So according to the well-defined of this part, and the reversal part is also under the vector addition, x plus y minus of x dash plus y dash equal to, that is x minus x dash plus y minus y dash. Okay. And at the same time, x plus y and minus of x dash plus y dash. So both image of the elements are equal. X plus y of plus w equal to x dash plus y dash of plus w under the vector addition. Under the scalar multiplication, ax, okay, ax, a of x plus w equal to ax plus w, a of x dash plus w equal to a dash x belongs to w. So when the both scalar multiplications, it is also well defined. Ax minus ax dash can also be written as a of x minus x dash belongs to w. So those scalar multiplications must be equal. Then easily now it easily to form a well defined of this part. Okay. Now here the direct of this part, a of we are taking any two elements x plus w and y plus w, in between x plus y of plus w, under the scalar multiplication, a of x plus y plus w means a of x plus y plus w. Now it can also be written as ax plus ay plus w is there. And that scalar multiplication can also be written as under the vector addition, ax plus w plus and again ay plus w. And again, that scalar elements taking it outside, a of x plus w plus a of y plus w is there. Okay, please stay on the line. And again, a plus b, there are another scalar is b is there. So scalar elements must be added here, a plus b of x plus w, that is a of x plus w plus b of x plus w. Under the multiplication, ab of x plus w, that is ab of x plus w, and can also be written as scalar multiplication can also be written as a of bx, and at the same time a of bx plus w, and again those scalar elements under the unity element 1 of x plus w equal to 1x plus w. So that values are equivalent to x plus w means this is the coset of the element, because 1 be the multiplicative identity. Okay. So finally v by w is a vector space over the field elements. Students, listen carefully. Quotient space, sometimes that is also called vector factor space. Please note down, quotient space or factor space. Okay, factor space or the space of residue classes, or the space of residue classes. So quotient space is denoted by v by w. So simply v by w means this is the construction. When it is the v by w to form a vector space, then that is the simple concept. Vector space means v by w under addition is an abelian group, v by w under multiplication, scalar multiplication holds good, and third one says distributivity conditions to satisfy any two is there. Okay. So before that already we have derived here. Okay. So this is one of the important theorem. Dimension v by w equal to dimension v minus dimension w. Please note down in the final examination 3.3.3. This theorem is very, very important in the final examination. Let W be a subspace of a finitely generated vector space capital V over a field capital F, then W and V by W both are finitely generated. When the W means a subspace, V by W is the quotient space. When the both are finitely generated, then the concept is dimension V equal to dimension W plus dimension V by W. In the same manner, or it can also be written as, just you have to see here. See here, this condition, dimension V by W equal to dimension V minus dimension W over F. Or dimension V equal to dimension W plus dimension V by W. Okay, this theorem is very important in the final examination. Don't forget this one. Okay, this is also one of the important theorem. And this is the worked out the above theorem to follow the one of the problem is here, dimension V equal to dimension W plus dimension V by W. This is also another one. Okay, 3.4.1. Okay, that is not necessary here. Okay, so this is the end of the third unit, because this theorem is very important in the final examination. Don't forget this here. Dimension V equal to dimension W plus dimension V by W. Because at the same time, that can also be written as dimension V by W equal to dimension V minus dimension W. So according to this principle, let us discuss one of the problem is there. Here, V be any one of the vector space. That vector space is given, subspace is given to write as the dimensions. So the number of elements given in the basis of the number of bases given in the vector space, that is called the dimension. Okay, so number of bases is given in the vector space. Suppose 3 elements are there. So subspace there are 2 elements are there. So what is the dimension V minus dimension W? 3 minus 2. So finally V by W means that is the representation of quotient space. This is the representation of quotient space. Okay, that quotient space of the dimension is, this value is 3 and this value is 2. 3 minus 2 is 1. So finally dimension V by W equal to 1 is there. Okay, that is the simplest problem for the given the objective type. Okay, through this theorem. Okay, now this is also one of the important theorem. Students listen here, because this is the end of this unit. Don't forget this one. In the final, these 3 units, in the final for these 3 units, to take the for how to give the questions in the final examination, there are 2 important concepts here. There are 2. Each first block is also, there are 2 given in the short notes, and 1 essay is given. Don't forget that essay already previous papers are also just you have to refer here, because define vector space, give example briefly. Define vector subspace with briefly. Briefly example is also briefly is here. Okay. Now prove that a necessary and sufficient condition, alpha plus beta belongs W and A alpha belongs W, that is the 2-step test for subspace, and A alpha plus B beta belongs W, that is the 1-step test for subspace. The intersection of any 2 subspaces is a subspace. The union of any 2 subspaces is a subspace if and only if one is contained in the other. Define linearly dependent and independent, and to practice the along with the definitions of the problems, to practice the problems from dependent linearly, LD and LI. LD means linearly dependent and LI means linearly independent. Okay. Now define quotient space. Define quotient space or quotient set to give the examples, or are the set of all cosets to form a vector space. The set of all cosets to form a vector space, that is called quotient space, that is denoted by V by W. So quotient space is V by W equal to set of x plus W such that here x belongs to capital B, or set of W plus X such that x belongs to capital B, either set of all right cosets or the set of all left cosets. Don't forget this was the students. V by W under addition under multiplication, that is the quotient set. The quotient set to form a vector space, that is called quotient space. Prove that dimension V by W equal to dimension V minus dimension W. Dimension V by W equal to dimension V minus dimension W. This is 3.3.3. This theorem is also very important in the final examination. Don't forget this one. Okay. Now this is the first block. Okay, please join the line. Now this class is up to 120 because some due to the power problem. Now that is the linear transformation. This is the second block. Linear transformation. What is the linear transformation? Now directly is simply understood here. Okay. Transformation means that is the one of the mapping. Let V and W be any two vector spaces over a field capital F. Students, listen carefully. Now in the examination from this block, how to give the questions in the final examination. Define linear transformation or linear mapping or homomorphism of vector space. Okay, there are similar names. Let V and W, there are two vector space over a field capital F. Now to write as the one of the mapping, F maps V to W. It is when it is that mapping is called a linear transformation. So what is the linearity condition? F of A alpha plus BW B beta. F of A alpha plus B beta. Now here given the mapping is F maps V to W. Here alpha and beta, there are two vectors given in capital V. Here A and B, there are two field elements. So those elements are scalars. To write the linear, scalar multiplication through the vectors alpha and beta, A alpha and B beta. Those scalar multiplication to form a linear, that is A alpha plus B beta. Okay, that A alpha plus B beta is also belongs to capital B. So, but then their functional element is represented as W. That is F of A alpha plus B beta is on W. That is the image of the part. So to write the linear condition through the functional part, A into F of alpha plus B into F of beta. Please note down. Now this is the rectify this mistake. Please rectify this mistake. This element is alpha, not V. A into F of alpha plus B into F of beta. So this is called linear transformation definition through the linear functional. Either linear transformation or linear functional is there. Here alpha and beta referred as the vectors, and A and B, there are two elements given in the field elements. Okay. Now just you have to see and refer. There are some more examples of linear transformation. So given the linear map is F maps R square to R cube, because that is the two-dimensional of the part is domain, and that is the third dimension, means the dimension 3 is there. Dimension of R cube is 3 because it is consisting of 3 coordinates given in this image of this part. Now when the domain of the dimension is 2, because R square is given in the domain of this part. So dimension of R square is 2. Dimension of R cube is 3 because it is consisting of two elements, means A and B. So to write as one of the ordered pair, F of A and B equal to R cube means there are 3 coordinate vectors. A, B, 0. So given the linear functional must be matched given the given of this part f of a and b equal to a, b and 0. There are three coordinate vectors given in this image because the dimension r cube equal to 3. So that's why it is given a, b, 0 is there. F of a equal to a, b, 0, linear functional part matched here. Suppose to write as a1, b1 and a2, b2. There are two elements a1, b1 and a2, b2. There are two elements given in the vectors. Okay. A1, b1, a2, b2. There are two vectors given in the functional part. So a1, b1, 0 and a2, b2 is there, another taking element. So that's why f of a2, b2 equal to replacing by the definition a2, b2, 0 is there. So f of a1, b1 equal to f of a2, b2. So a1, b1, 0 equal to a2, b2, 0. A1 equal to b1, a1 equal to a2, b1 equal to b2. So we have to write as the f of a alpha plus b beta. So f of a1 b1 plus f of a2 b2 is also satisfied through the linear property. And scalar multiplication is also there. Okay. To take the xb any one of the scalar, f of ab equal to x of, here x being the one of the scalar, x into f means x of ab 0. So the scalar multiplication must holds good. There are direct condition must be satisfied through this one. Here alpha equal to a1 b1 and beta equal to a2 b2 to write as the a into f of alpha plus b into f of beta. So that's why given this example must satisfies as the linear transformation. And through the matrices example is also there to write the another linear transformation example 4.2.3. 4.2.3, because in the examination is given define linear transformation and give one example, or give example means only one example is there. Give examples means there are two, you must write the two examples. Okay. Now this is the elementary properties of for linear transformation. Okay. Please stay on the line. That is 4.2.24. This is the under the definition of properties. Okay, from the definition of linear transformation to write the elementary properties and some basic properties on linear transformation. T of 0 bar equal to 0 bar. Here 0 bar represents the domain of this part. Here 0 bar is also referred as the, what is this? This is the image of the part. So transformation of 0 bar equal to 0 bar and image of an inverse equal to inverse of the image. T of minus alpha equal to minus into T of alpha. To write the linear combination on linear transformation, that is T of a1 alpha 1 plus a2 alpha 2 plus so on an alpha n equal to a1 into T of alpha 1 plus a2 into T of alpha 2 plus so on an into T of alpha n. Now these are also three simple properties on a linear transformation. Okay, don't forget this one. Okay, that is the simple examination, simple questions given in the final examination. Okay, zero transformation means 0 maps v to w, 0 of alpha equal to 0, that is called zero transformation. Define zero transformation and identity transformation. Identity means I of alpha equal to alpha, because the linear functional is also depends upon the identity mapping. I maps v to v. When the domain and codomain of the vectors is same, I defined from v to v, because I be the identity mapping. So we are taking the one of the domain element is I of alpha equal to alpha. So that's why this is called identity transformation. Identity linear transformation. And through this zero transformation is also a linear transformation, because that is the definition from 0 maps v to w defined by 0 of alpha equal to 0, because that is called the zero transformation. Okay, thank you. All right, time is over. Don't forget this one. Okay. Please stay in the line. So identity zero transformation and identity transformation is also a linear transformation. Okay, students. Anyhow, time is over already. Some due to power problem, some disturbance. First 10 minutes, some disturbance is there. So that's time. The time is also balanced here. No problem. You must watch through the online or through the YouTube and thoroughly for your convenience purpose especially, because through the subject and easily to understood and easily to face the final examination. Don't forget this one. Okay, next we will meet again in the next class, or maybe tomorrow or next week. Okay, anyhow, once again wish you all the best and wish you good luck. Please note down once again, my number is also please be noted here. If you have any doubt for subject purpose, okay, please contact us and personally through WhatsApp, and I will give some other advices, some other suggestions also there. There is no problem. At any time, I must respond here for your purpose. Okay, please note down my mobile number 9989476833. Okay, thank you one and all. Okay, thank you.